So now I want to explain about the covering property of the complex exponential map. So it should be clear from the last video, the complex exponential map behaves more or less the same way as just this, as by this sort of vertical projection from this helix here down onto the annulus. So if we take it, I mean, this helix here is just like a band in the complex plane, a sort of vertical band. But it's just been curled up, which doesn't really change anything. And then if we apply the exponential map to that, then the sort of the whole thing gets collapsed down like a pancake onto this annulus here. And so the point about a covering map is that if you take a small patch on this kind of downstairs thing on the annulus, then the pre-image of that patch is a subset of this helix. And it consists of a whole bunch of disjoint individual copies of that small patch. That's basically the definition of what we mean by a covering map. And if we move the patch around here, then the corresponding family of patches moves around the helix. And if you follow any kind of individual patch here, right, any one individual patch like this one here, as we go around, so that patch moves and it moves and it moves, and you go all the way around, then it kind of this patch will go, because this is kind of going down in this clockwise direction. If we move this patch around here, then the corresponding patch on the helix will move down by one layer in this helix. But if you look at the whole collection of patches taken together, it's exactly the same, right? I mean, it's the way the individual patches line up is different, but the whole collection of patches here is the same as we move this patch all the way around the annulus. This kind of works with a small patch, but it also actually works with a bigger patch. We can make it bigger like this, and it's still true that if we've got any patch like this, then the pre-image in the helix consists of a whole bunch of just disjoint copies of this patch here. Okay, so you've got like one copy here, and then another copy there that's completely disjoint from it, another copy there that's disjoint, another copy there that's disjoint, and so on. It still works however big we make this patch, so long as it doesn't kind of go all the way around. You can make it go nearly the whole way around the annulus with just a small gap. Okay, and then the pre-image here, you've got one segment like this that goes nearly all the way around, and then another segment here. It goes nearly all the way around, but it's kind of disjoint from the first one. You get again a stack of disjoint segments. Each component of the pre-image here is homeomorphic to this gappy band here. And so we get an infinite family of copies of the original thing. So that's what it means to be a covering map. And one of the key results that we have about covering maps is the path lifting property. So let's explain that now. Okay, so here we've got a path in the annulus, sort of starting at this black dot here and going kind of 1.5 times round to get to this black dot here. And we want to lift this path. We want to get a kind of corresponding path on the sort of spiral staircase thing that projects down onto this path we had here. So firstly, we have to sort of decide where to lift, where we're going to start. I mean, here you've got this whole stack of dots here. These are all the possible pre-images of this initial point here. We have to pick one of them where our lift's going to start. So we're going to start by lifting at this point. It's been marked in blue. So now we just take a very short section at the beginning of the curve here, and there's an infinite family of different ways to lift that short section, as shown in the picture on the right. But only one of them kind of starts in the right place at this blue dot that we've chosen to use as our initial lift of the initial point. Okay. So we have to use that section. Okay, we're going to use that section. We've now marked that in dark blue because that's part of our lift. So then we look at the next section. Okay, so we've got the next section here shown in red, and then we've got an infinite family of possible lifts of that red section over here. Of course, only one of them actually lines up with the blue section that we've put in already. So we have to reject this one and this one and this one. This one we have to just select this lift here so that it lines up continuously with what we've already done. So we fit that in, and then we go on to the next section, and again we have infinitely many choices, but only one of them lines up with what we already did, so we have to select that one, and then we carry on the same way. You just go all the way around, lifting, lift short sections of the curve one by one. Okay, and this is kind of working because yeah, it's a covering map, and so we just take any short section. That's going to be a short section of curve that's contained in a trivially covered open set. You know, the part of the spiral staircase lying above a short section like that is just infinitely many disjoint copies of the downstairs bit here. Okay, so we can just carry on like this all the way around and around. And a key feature of this is that, you know, here the curve's gone basically once around the annulus, but the lifted curve doesn't close up. Right? We've gone one rotation basically, and that means that we've gone kind of up a floor in the spiral staircase. And then we carry on like this. Again, sort of we're now sort of always running one one floor up from where we were the last time. We were sort of roughly over this spot. And then at the end of the day, we get to this point here, which is one of the possible lifts of the end point of this curve.